Okay. Hi everyone, welcome back. I'm sorry for being a little bit late today. We should have a bit of a shorter lecture today. We're going to be going over branching and how you can translate branching instructions in simple IR into the corresponding assembly code. Does anyone remember what kind of assembly code we're using in this course? AT&T. For what architecture? x86, 64-bit. Yeah. Cool. So I want to begin by going over the homework. I guess before the homework, actually, any questions? Anything we reviewed so far? Any questions with the project? Okay. I think at the end of the lecture today, I'm going to also go over a bit more about C++, just what you really strictly need to know for this project, because I think maybe many students are unfamiliar with C++, and it'll be your first time using it. So I'll just go over the broad strokes of what you should be aware of. That'll be probably pretty brief. So for this question, the x86-64 instruction set's IDIV operation for division only takes a single argument, i.e. IDIV, the B register. What is this, or why is this, and how do you set the other argument? So, yes.
So the dividend for IDIV is stored in the RAX, RDX registers, and in order to set the dividend, you need to move whatever value you want to those registers, but you don't pass those registers are hard coded.
Yeah, it's hard coded at the RDX, RAX register, sound extended registers. Will be the numerator for the division. How do we actually perform the sound extension, combining the RDX and RAX registers? What instruction do we use? CQO. Convert quad to octo, presumably. Okay, so I think that's it for the homework question. Did anyone start implementing the arithmetic methods for the compiler since our last lecture? Yeah. Okay, cool.
The arithmetic operations one's the hardest one, like out of all of them.
Which one?
The arithmetic operations.
Yeah, I think the arithmetic operation is probably the hardest one. The branching ones are not quite as hard. Did you do the branching yet? Or yeah? Okay, cool. So this lecture will be a review for you. Great. All right, so today we're going to go over, again, branching. We're going to be looking at unconditional branches, so strict go-tos, and also conditional branches, like branching on when a certain condition is met, like comparing a value to another value, for instance. So we'll be going over today. Yeah, so today's lecture, the goal is to translate simple IR instructions in this form, where loop, : is a label of the name loop, and then go-to loop is just a jump statement, essentially, in the corresponding assembly code. So, can anyone tell me what a label is?
I don't know the technical terms for it, but it's a place in your code that you can jump back to.
Yeah, it's a named location in code. That's it. How do we think labels are implemented under the hood? What do we think the CPU or the CPU is doing? Anyone remember from computer organization what we use for executing code? Yeah, and where exactly is the current location of the current instruction stored? What do we call that? The what?
Is that the program counter?
The program counter, yes, the PC. So really all a jump is doing is just setting the PC, the program counter, to a specific label, whatever memory address, instruction address is associated with that label. That's all we're doing. Yeah, name locations in code. So one more important thing to note here, just to remember, is that in assembly and in simple IR, these labels, they fall through. Execution proceeds through a label to the next line of code. So when you see a label, it's not like execution is going to branch anywhere immediately. Execution will just continue past that label. So first we'll look at unconditional branching, which should be hopefully pretty simple the jump statement. All right, yeah. So all unconditional branching really does is, there's really not much to even explain here. When you see a jump, that will literally just, like I said earlier, change the program counter directly to whatever label you give to the jump statement. This will be pretty simple to implement for your compiler. I'll show you some examples of how to implement one of these methods at the end of the lecture. More interesting are conditional branching, conditional jumps. So for instance, here in this C program, we call x equals readInt. Then if x is greater than 10, we set x equal to 11. Otherwise, we increment x by 1 and then call printInt passing it x. So these are actually the two functions that are defined for you in the iolib.c file that's given to you with your compiler project for testing your code. The corresponding simple IR code would be making a call to readInt using the call keyword. And if x is less than or equal to 10, we go to the false label, increment x by 1, set the result to the result of calling printInt x, and then returning 0. Does anyone notice a strange thing we've done here? What's the most salient thing, I guess, that we've done when translating this condition?
You like do all of the variables that you set them up all at the beginning? Like that's
What's one difference between the original C code and the simple IR code? Yes?
You swap the condition, you know what I'm talking about.
Yes, we inverted the condition. So the condition here in the C code is x is greater than 10. But in the simple IR code, we have x is less than or equal to 10 instead. So often you'll see this. You don't have to do this when implementing your compiler, but often you'll see compilers do this. When they're converting from a structured language like C to an unstructured language like assembly, and by unstructured I mean there's no blocks, it's just straight line code, these conditions will be inverted. This is to allow you to admit fewer lines of code in the translated assembly code. Makes the result more concise, which usually saves CPU cycles and makes the code faster. But I think when we're implementing our compilers, you don't have to do this inversion of the operators. Just know that sometimes you'll see this. It's just for performance optimization, essentially. Yeah.
wait, so like it goes faster, but like do you mind me explaining how to make it faster?
There will be fewer instructions. If I were to try and implement this, we can try and implement it now. Well, this example may not be a good example. We'll go over some at the end, actually. But the big idea is by inverting this comparison operator here, so less than or equal to is the opposite of greater than. This is greater than. The opposite of that is less than or equal to. We can actually emit fewer instructions in this simple IR code. The branching becomes simpler in the translation.
Oh, okay.
Yeah. Yeah.
So that's not necessary though, right? It's just like for easy to use, I guess you could say.
Yeah, yeah. I mean, you can, in our compilers, we'll be doing this a simple way, which will be to keep the condition the same as it is. Okay, so refresher quiz. How do we access the variable x's data? What's like the broad way of doing it? Big idea of how you access a variable's data in assembly code. That's how we would move value into or out of x. But what specific memory address do we use? How do we reference its memory address?
We need like the base pointer or something like that, and then we need to subtract like the bytes or the bits to get to the data section.
Close. So what's that word? The
Offset?
The offset, yes. So we use the symbol table, which we don't have here. Here we go. Now we have one. So what you would do is take the base pointer, which points to the base of the stack frame, which contains all the local variables and parameters for a function. And you use the symbol table, which is given to you in your compiler, to get the offset of that for that variable from the base pointer. And then you simply apply that offset to the base pointer like this. So remember, it's sort of the opposite of C syntax. In C, we'd have array name followed by the address. In assembly, it's offset followed by effectively an array name, basically, the base pointer. Okay, so to actually perform our conditional branching, we need a way of comparing values to each other, because you saw back here, we're doing comparisons, and we're branching based off the value of x in relation to 10. So we need a way to actually perform comparisons. Oops. Yeah. So the way we translate these sort of relational operators, less than, greater than, less than or equal to, etc., is using this compare instruction, which will set some special flags on your CPU, some special registers for flags storing the result of this comparison. And then with those special flags, we can perform different kinds of branching instructions to actually read those flags' values and jump appropriately according to whether or not according to whatever the comparison instruction returned. So here we're comparing RBX to RAX, and then based on the result, if we found that RAX was less than or equal to RBX, we would jump to the false label in this case. Let me think if I can see if I can give an example here. Okay. Yeah. So in this case, we have the simple IR code. If x is less than or equal to 10, go to false label. And the assembly code here compares RAX to RBX, and then jumps if RAX is less than or equal to RBX. So note the operand order. This is important. RAX is the right operand for the comp instruction, but it's the left operand logically when we're doing the comparison. So the way to think of it, the way that I like to think of it, oops, here we go, is that the comp instruction like this, RBX, this is sort of equivalent to setting us up for any kind of comparison of the form RAX question mark RBX, where question mark could be any operator, less than, greater than, less than or equal to, less than or equal to, greater than or equal to, etc. That's really what this comparison instruction is preparing you for. And then to actually branch based off what this operator has to be, we have access to all these different opcodes here. So jump equal, jump not equal, jump less than or equal, jump greater than or equal. All the ones that involve 2 characters on the right have 2 characters on the left, or 3 characters on the left. That's like a quick way to remember them. So comparison for equality only has E, JE. Comparison for inequality has JNE. Less than, JL. Less than or equal to, JLE. So hopefully the mnemonics are kind of intuitive. They're meant to be. But any questions on what these mean? Let me see what's next here. Okay. So for us performing our conditional jumps in our compiler, we can follow this specific template here. So again, we're going to have access to the grammar file, which tells us what fields are available on each context object we're taking in our visitor methods. And we can use those to actually emit translated assembly code according to this template. So just like before, we set up our operand, just like we do with arithmetic operations, we set up our operands in the RAX and RBX registers, then we actually perform the comparison, and then perform the actual appropriate jump. Okay, so I guess let's see a full example. Any questions before we continue? Yeah.
No, I answered my question. I was gonna ask what the false label was, but I'm guessing that's like else.
It's just a label we've written here explicitly. So right here, this is just a label called false label.
Oh.
So anywhere in your simple IR code, you can just write a name and then a colon and then jump to that label. You can even do this in C code. There are labels in C code as well. We saw that, we should have seen that in the proc project. In the MyShell template we gave you, there was labels all over the place. So, okay. So for this example, we have if x is less than or equal to 10, go to false label, x is equal to 11, the false label is here, and then x is equal to x plus 1. Let's see the assembly translation. So if x is less than or equal to 10, go to false label. We set up our operands, so we're assuming that x is at offset negative 16 from the base pointer. Why is it negative? Why is the offset negative?
We-
The stack grows down, exactly, yeah. So we're moving from negative 16 RBP into RAX, negative, or 10 into RBX. For the comp instruction, will it be compare RAX, RBX, or will it be compare RBX, RAX? Which one do we think the comp instruction will, if I can get this here to the left, there we go, okay. The bottom one? So RAX stores what? X, right? The left operand. So yeah. Yeah, this is the correct one. So X should appear on the RAX should appear on the right because the operand we're comparing X is on the left. So you just swap the order of the operands when doing the comparison. If that's a little confusing, another way to think of this is sort of like subtraction. Essentially what the CPU is actually doing, the ALU, the arithmetic logic unit, is actually performing a subtraction of A register minus B register, and then setting some flags appropriately according to the result of that subtraction, whether or not it's negative, things like that, or it's 0. So now if the result is less than or equal to, so that's if the result we find is less than or equal to, then we branch to the false label. And then for the assignment, we just do what we've done before. We move this immediate value into the A register, move the A register into the value of X. And why do we perform this seemingly useless intermediate load here, or move? Why do we do this in our compiler? Why don't we just move 11 directly into negative 16 RBP?
You were speaking about if you want to change something, it would be hard if you did not that, because then you have to change this instead of template. You can't
Yeah.
template as easily.
Exactly, it's just for the template. You could make what an optimizing compiler would do, a compiler that tries to make your code as fast as possible would do. It would just change this out for 11 into negative 16 RBP, remove this instruction here. But for your compiler, it's easier for you to implement if you just follow a template for everything. So we're normalizing this by moving 11 into RAX. This lets us replace 11 with some other memory offset, some other register value, etc. Yes?
So compare is kind of like just getting you what happens with X and 10, and then you can use the next line JLE, and that's the actual like command afterwards, and it just gets that from the CF.
Yes, yes. So you always want to follow, pretty much always, you just want to follow like the jump instruction or follow the comparison instruction immediately with the associated jump instruction. And you can use JLE, you can use JGE, you can use JG, all the other different jump operations that we have. And finally, the false label is just false label. So it's a one-to-one translation between simple AR and assembly for the label names. Yeah.
So, as far as the false label, I mean, it operates whenever the argument is false, but could you make it to where it goes to that operation if it was true, or would that also be considered a false label, or?
Well, this is just a label name. We've written this label name. I'll go back up here. We've written this label name directly into our code. We can jump to it based off whatever we want. We can do whatever operation we want to jump to that false label.
So just like a marker, basically.
It's just a marker. Exactly. Exactly. A label is just a named location in your code. It's up to you, the programmer, to choose how and when to jump to it. much that doesn't fit, but I think for this you can also get the idea. We've seen this before in the arithmetic operations on the previous lecture. Make this a bit bigger. So here we're saying x equals x plus 1. We're loading the value of x into the A register, loading the value of 1 to the B register, performing the addition. Where is the result of this addition stored? RAX, the A register. And then we're moving from the A register into the base pointer, or an offset from the base pointer where the x variable is. Any questions? Okay. All right, so now I want to go over some examples of converting C code to simple IR. We won't be compiling C code to simple IR with our compiler, but you should know how to convert C code to simple IR. You might receive a quiz question on this. I have prepared exam questions about this topic. I haven't always given them on exams, but be prepared to potentially convert C code to simple IR, just to show that you understand how this compilation process works. So the first one we're going to look at is if then else. So let me open up a file here that I prepared. I think I prepared a file. Yeah. All right. So we have some C code here on the left. Going to open a file here on the right for us to convert this to simple IR. So if we want to convert this C function to simple IR, what's the first thing we need? Yeah.
Function name.
Yes, we need the name of the function. So consider this like a bringing everything together review, what we've seen so far. How do we end a function in simple IR?
Function in.
End function. I think it's just end function. What's the first thing we need to specify? Local variables. What's our one local variable here? X. Do we have any parameters? No, so we can skip specifying them. Now what we want to do is load the value 1, or 4, I should say, into X. So what instruction can we use to do that? We don't have to do it like the compiler. We can use shorter instructions, if fewer instructions if possible. Okay, so we're going to use the move instruction. How do we specify an immediate value, a literal value in assembly, or a simple IR? Oh, sorry. I did this last semester. I'm almost going into assembly mode. We're actually doing simple IR. So we're just assigning. So sorry, we're in simple IR, so it should just be an assignment. Yeah. Okay. So for the if statement, for simple IR, we're comparing x to 5. So we'll use an if goto. That's what we call this construct in simple IR. In the grammar file, it's called if goto. So we'll say if x is less than 5, go to, and we need a branch. So we'll just say true label. And here we can say true label. X equals x plus 1. And now, let's see here. It's not our return statement. We'll just return 0. And we need a false label as well for executing when the code is not true, for when x is not less than 5. And does this seem correct?
No.
No, right? So how can we fix this? What's something we could do to make this work?
Directly after if, call go to false label.
Okay. All right, so now if this condition is not satisfied, if x is not less than 5, we proceed to this line, we jump down to false label, We execute these lines of code and then return 0. So that seems to work. But there's still something wrong here.
We could use another label for like end, and then have directly after the true label or after the statement in the true label say go to end.
Yes, so right now, if we do branch, we'll branch to the true label, then we'll keep executing because assembly code is one line at a time. We'll keep executing from here, continue to the false label, and then perform the false label anyway. So we want to avoid doing that. So we'll say go to end, and then we can add another label right here called end. Yeah.
Do you necessarily need the false label, or could you just put x equals 7 where you have go to false label?
We could do that. So that's another idea. We could say x equals 7, but then we would still have a bit of a problem here. What do we have to do now?
Go to end.
So we need to move our go to end up here now. And then we don't need the false label. So you're kind of seeing the idea. There's different ways to implement a compiler for these sorts of or branching operations. They each have their own virtues. So if we were to invert this condition, let's say greater than or equal to 5 like we saw before, put the false label back. And then we no longer need the true label. So, different ways to do the same thing. So here we've inverted the condition, so that way if this is true, we go to the false label and then fall through to the return 0. But if it's false, we continue to x equals x plus 1, and then here go to the end to skip the false label. Yeah.
Probably not part of the scope, but I'm still wondering why does inverting it make it more faster?
If you had nested operations here, like nested arithmetic operations, okay, maybe I shouldn't say faster, we'll make the code smaller, which often can lead to improvements in performance. But you'll see we were able to remove like an extra label by inverting the condition here. Whereas before when we had the true label, in this case, we just had to have more lines of code. So our compile result was just larger. There was more lines of code in the compile binary, or compiled assembly code. And that usually can lead to slower performance. I shouldn't say it always will, but sometimes it can lead to slower performance, having a larger piece of code. Okay, so any questions about this single example here? All right, so now I want to go over one topic that I'll bounce back to later. Control flow graphs. So this is something that, again, you don't necessarily need to know in this course, but it's something that you should probably be familiar with, especially if you want to go into security and control flow analysis or anything related to that realm of computer science. There's ways to model and visualize the control flow, the flow of execution of a program, using what are known as control flow graphs. So in this example, we have a simple control flow graph for this code here on the left. If x is less than 10, x equals 12, and then return 0. The way to model these sorts of control flow is to create a box for each condition and then statement, and then just draw arrows connecting the flow of control between these different conditions based on what actually executes, what conditions are true. So in this example, we have if x is less than 10, that's the first box here. Then set x equal to 12, so we branch to x equals 12 on the right. Otherwise, we skip to the return 0 statement here at the bottom. And after assigning x to 12, we also go directly to the return 0 statement here at the bottom. So you can apply this to your assembly code as well, your simple IR code. It's not limited just to C code. It's just a way to visualize the flow of control throughout your program. Okay, So we'll see more of this soon. I just wanted to show this briefly before we continue to the next example. All right, so let's see what else is here. Yeah, while. So here's another example. I guess actually the last example. So here we have a while loop. So let's clear what we have so far. Set that x equal to 12. How can we implement a while loop in simple IR if we don't have like blocks or structured programming constructs? Yeah.
So you can use an if statement with the inverse of the case in a go-to that breaks out of where you would think the loop would be, and then at the end of the loop you have a go-to back to the if statement.
Yes. So essentially what we need is a label for the top of the loop, and then we're going to check if the loop's condition is true. If it is, we continue executing the loop, and if it's false, we break out of the loop, essentially. So we'll say if x is greater than 5, go to, we need a label, we'll say end. And now inside the loop, oops, delete that colon. Inside the loop we can do is set x equal to x minus 1. Sorry, this should be inverted. And then how can we go back to the top of the loop here?
Go to top.
Go to top. So this is the big idea for how you'd implement a looping construct in assembly code. Can anyone tell me how we could implement a for loop then, compared to a while loop?
Wouldn't you just like initialize like at the top, you'd initialize like the I variable and set it equal to 0, and then have all of the conditions based off of I instead of X?
Sure. So let's say for, I'll declare the int I up here. I equals 0, I is less than 5 plus I. Now in our assembly or simple IR code here, we'll have to say declare I as well. And then what we would do is we would add some extra lines of code where at the top of the loop, before the loop even begins, we set I equal to 0. We check if I is less than 5. And then at the end of each iteration, before we go back to the top, we add this line of code, x equals I plus 1. Or I equals I plus 1, I should say. Yeah.
Would it not be I that equal to or greater than 5?
Oh yeah, good point. Gotta invert the condition. Yeah, good catch. So now if I is greater than 5, we break out of the loop. Otherwise, we continue executing the loop, incrementing x by 1, and then decrementing x by 1, incrementing I by 1.
Done explicitly, or is it just like preference?
Inverting the condition, or?
No, the name top.
Oh no, that's just kind of a convention that we had in this course. I don't know what they actually give it, what name they give it in compile code and actual compilers.
Okay, those one. I think in C they always just say loop.
Mm-hmm. So hopefully you're kind of getting the big idea that with simple additions to these translated constructs, we can support more and more complex looping mechanisms, or really just more and more complex constructs in our original programming language or high-level language. So we don't have to do this one now, but let's go back to the while loop. Can anyone tell me how we would implement a do while loop? What's the modification we'd have to perform? So let's go back to the original while loop code here.
You have the if statement take place before the top, and then instead of it put the link to the top, and then where top is, you put end.
maybe. Let's say, what's like an even simpler way to do this? What's a very simple way? Yeah. Yeah.
Could you hypothetically put the if statement at near the end of the loop? That way the code guarantee runs once and then it can check if it should stop or continue going.
Sure, that's another idea. Yeah, put it at the end of the loop instead. That works as well. Yeah.
Do you not keep the same as before you make that change, but just put the x equals x minus 1 before as well?
That's probably the simplest way to do it. You just run the code once, definitely, before you even start the loop. Yeah.
But you should also just, instead of having a word condition, just have a condition to return to the top instead. So like instead of go to top, you have if x is greater than 5.
Sure, so let's see that. So if x is greater than 5, go to top,
And remove the bottom or replace it with the
or replace what with the if?
So move that one on up and then delete the root top. Like just the base.
Sure, I think that works. Yeah. So again, the point is just to get you thinking that there's different ways to implement a compiler. So if you're interested, you can look at the source code for a lot of different compilers. A lot of them are publicly available. They're all like open source. Like GCC is actually open source. CLang is open source. Clang is open source. All different C compilers. And if you find all of this interesting, I recommend taking COP, I think 5621, compiler construction. My advisor, Dr. Gazzillo, teaches it. He doesn't always teach it every semester, but when he does, just you can check and find it. And if you find this sort of stuff cool, you can look into taking that course with him. In that course, he'll go over what are called peephole optimizations, which are very small optimizations you can make to your program's compiled output just by looking at its just looking at it. So it's very simple analysis you can do to optimize your code, make it faster. Okay, any questions before we continue? All right. So some more about control flow graphs. This is kind of similar to what we just saw in the if then else C file. So in this case, we have a condition that either has a true branch or a false branch, if and else. Conventionally, in these control flow graphs, the true statement is given on the right and the false statement is given on the left. So you can see when there's an if-else statement, we have this divergence here and then convergence back to the return 0 afterwards. And then finally, if we have a looping construct, you can just implement this or diagram this as such where the statement after the loop can either go back here or here. And actually, there's a bug in this diagram. Can anyone tell me what it is?
You don't give a value to x.
So that's true. We don't give a value to x. But what's wrong with the diagram itself? The diagram's control flow is actually not necessarily accurate. There's a flow that it's missing.
If x is greater than 10, it never, well, it can't hit return.
If x is greater than 10, it will never execute this line of code. Or it won't go to x equals x plus 1. Yeah. So if x is equal to 11, we would actually skip this executing this block here and go straight to return 0. So we're not accounting for that in this current iteration of this diagram, so I'm going to add that here. So again, if x is equal to, say, 11, because we didn't initialize, it could be any random value. If x is equal to 11, we would actually skip executing this line of code, x equals x plus 1, entirely, and just go to return 0. So you might be asked on an exam to interpret one of these diagrams, but I won't ask you to make one necessarily. Yeah.
Would you be willing to do that for extra credit?
I'll consider it. It's just that, to be honest, having students draw these sorts of diagrams and grading them all doesn't scale very well. But this class is smaller, so maybe. Okay, any questions on anything here? Okay, I'm going to save this diagram. So I just fixed a bug in it. And let's take attendance before I go over the compiler project some more and some of the C++ idiosyncrasies you should be aware of. Stop recording briefly. Okay, so let's go back to the lecture or compiler project directory here. And let's just go over briefly the compiler project again. So again, you'll be given this starter code with a codegen.cpp.template file. You'll want to rename this to codegen.cpp. You'll be implementing all of your compiler methods in this file. Oops. Okay, I'll zoom out a little bit here. Okay, so I guess I'll just go over really what you should know about C++ first. So again, we have include statements just like in C. This C++ uses a C preprocessor just like C does. A difference you'll see is that some headers don't end in .h. These are going to be standard headers in the C++ standard library. But sometimes you'll see that they do sometimes end in .h. Those are going to be C headers that C++ has access to. Again, just like in C, headers that are enclosed in double quotes are local headers that you can include from your local current working directory. This using namespace keyword is the first new syntax you'll see in C++. What this basically means is that we're allowed to access any functions or variables or structs or any other declarations that this ANTLER4 namespace provides without using the dot before it. So otherwise, if we wanted to access something like simpleIR lexer, I think ANTLER4 defines this, we would have to say ANTLER4.simpleIR lexer. So using namespace ANTLER4 prevents us from having to do that. Actually, I think I got the syntax wrong. It would be like this. ANTLER4 : parse tree. Which is pretty annoying to put all throughout your code, so in your implementation, we just use the using namespace keyword for you, or syntax for you. I will say that in practice, it's often considered bad form to use a global using keyword like this at the top of your C++ file because it pollutes your namespace with all these different declarations that you did not declare yourself. But for this simple project, it's simpler and easier for you to implement this code if we just use using here, so you don't have to type ANTLER4 : everywhere. Same thing with standard. To use any of the standard library functions, you have to use standard : So we just use the namespace standard to prevent you from having to do that. Okay. This map construct here may also be unfamiliar, this map type. So a map, I mean, you've all taken CS1 at this point, it's a prereq for this course. So you all should be familiar with hash tables. A map is just a hash table, fancy name for a hash table. These tags here, these angle brackets, they are just like in, I don't know, have you all taken processes or object-oriented programming? Have you all taken that course? So you're probably familiar with Java templates. Same thing here. This declares a map from strings to integers. This static keyword, this is also in C. It just declares a static function that's going to be compiled for this specific file. I won't go into that in too much detail. It's not really something you need to know. So you can see just like in Java, objects can have methods attached to them. So this method's going to be getting the type of the specific token, for instance. You're probably familiar with this with Java. Methods attached to objects. In C, we don't have methods. Structs only have fields. They don't have methods attached to them. They're just data. And the way we declare classes in C++ is with the class keyword. So this will say a class cogen, and it inherits from simpleIR base listener and it inherits publicly, which means that any of the methods that inherits from the base listener, actually I forget exactly what the public keyword means here. Yeah, I don't think in Java you have this public inheritance versus private inheritance. But basically the colon here means that we're inheriting from another class. You can think of it like extends in Java. These virtual functions mean that these methods can be, if a method is virtual, it means it can be overridden by a child class. In this case, it's kind of unnecessary because we're not actually overriding these methods later. And the override keyword here is also optional, but it just signifies that we're overriding a parent, a method defined in the parent class specifically. So you don't have to include this, but it's usually good practice because it lets the compiler tell you if you try to override a method that's not defined in the parent class and you put the override keyword, the compiler will tell you that you're trying to override a method that does not exist in the parent. So if I were to delete this and the parent did not have a method named enter unit defined on it, we would actually not get a warning. But if I had override here and the parent has a method named enter unit in it, then everything will work as expected. So this is really just a way to like have safe programming, defensive programming, using the override keyword. So for printing in C++, it's also kind of weird. We have this cout variable, this like file descriptor, or file pointer, I guess, file stream really. And we use this special syntax, the less than signs, to print to standard out. So less than, and then we have this string we're printing. We can also print variables. They'll all be formatted correctly when they're being printed to standard out. And then endl will just print the end line character, the new line character, and flush the buffer that you're redirecting to. Yeah.
So what would be the C++ bitwise operator for like left shift then?
So this is a problem with C++. It actually still is the less than. But with C++, you can redefine how certain operators work for different variables, different contexts, which makes C++ really hard to read at times because you have programmers who try to get clever and they redefine all the standard basic operators to mean different things for different variable types. So you'll see this in physics engines, for instance. This is a common example. Someone will define a struct vector. This is like really common in like C++ physics engines with int x, int y, and they'll redefine the plus operator to add the x fields to each other and y fields to each other. Oops. I don't even know the syntax for doing this because I avoid doing this, so I don't know the syntax for doing this, but you can redefine like how plus works between two vector structs to add the x fields of each other to each other and the y fields of each other to each other. Yeah.
Just make sure I understand. So shorthanding vector, or like vector.x plus vector2.x to just be done automatically by the plus symbol?
Yes, yes. It sounds cool, but there's a problem. What happens if you try to redefine the asterisk operator? Does anyone see? Can anyone tell me what the problem might be with this? Pointers. Well, pointers isn't the biggest problem. Has anyone taken physics? Does anyone know the two different ways you can really multiply vectors?
Yeah.
There's cross products and dot products. And the asterisk does not make it clear which one you're referring to. So this is why people sometimes really despise C++ because you can write very difficult to read code very easily by overloading all the operators that mean different things. So we're not doing that in this program. But the standard library has done it for you, overloading less than to mean print to this stream.
So how would you like read that in C-ish terms?
How would I redefine the operator?
Out with the,
Oh,
yeah.
you could actually just do printf, and we could say \t.file, and then %s. And don't forget the new line character. And this would be like basically the equivalent C code. The difference is that, oh, yeah, question?
Why would you ever want to redefine operators? Like, why not delegate that to a separate function instead?
Some people think it looks cool. Also, it saves you some space. It can save you some space. If it's used very carefully, it can save you some space and also make your code a lot easier to read in very like select conditions. But also, it's like a preference thing. So, like C programmers really don't like doing that because it makes things a little like very implicit. But some people who like to really modernize their code will do it sometimes for things like vector addition is pretty unambiguous. So maybe it's safe to do it there. Yeah, it's kind of a taste thing. Really, like when you get a job, like working as a software engineer, you probably want to check with your, if you're working in C++, definitely check with who you're working with as to what conventions they like to follow in C++, because everyone has their own different preferences with the language. Yeah.
My understanding is also useful for like if you define a custom class, then it's good to work it's like obvious what would be.
Sure. Yeah. And then the question is, what's obvious? That's always.
Like only one option that makes sense.
Yeah. Yeah. I see what you mean. Yeah. So. Okay. Let's continue, I suppose. So you'll see the auto keyword here. Auto just means infer the type for me. So here we're saying variables equals context variables. We don't have to specify the type ourselves. The auto keyword will automatically, at compile time, infer what the type of this variable needs to be, based off the type of the context variables field. This is another issue with C++ people like to complain about, is that if you use auto a lot, it's really unclear what types your program is dealing with, because everything's inferred for you.
Maybe Python.
Python infers it for you, but Python's a scripting language, so you could argue that its intent is a little bit different. Yeah, I don't know, but you're right. You're right. That's yeah. Okay, let's see anything else here worth pointing out. Yeah, different ways of opening files. This fstream variable. It's ifstream input file stream. Open it with the open method. Yeah, not much else. If you have other questions, you can ask me. I don't know. Is there any kind of burning questions you have about C++? Okay, because you're not defining any classes yourself, you're not defining any new methods, you're just filling in methods that are given to you. So hopefully it's not too bad. And just follow existing files as an example, existing functions as an example. I'll give you one more example here. This one's super easy, so don't think that I'm giving you anything really hard. Enter label. This one's, I think, pretty simple. The process of completing this, just to show you an example of how you complete one of these methods for the project. First, you'd want to open the simpleir.g4 file and look for the label grammar rule. So here's a grammar rule for label. We see it has one field called label name, which is equal to a name followed by a colon. So we can get that name with the context label name field. And we can get the text behind that label with the getText method. And then to print this out, to actually compile this, we can just say cout label name getText. Followed by a colon, and then end line. So that's how you'd implement the translation, the compilation from simple IR labels to assembly labels. Pretty simple, I think. Hopefully very simple. And now we can test this. I'm going to save and quit here. Run make. Okay. I think this is a pointer, not a static or automatically located variable. It's a pointer. So, okay, it compiles. Let's edit the template.ir file, which I went over last time, is given to you. So in here, we'll just add a label. I'll say some label. And now we'll I had added this rule last time as well to quickly compile our code and run it on the given template input. So this is all in the instructions for the project. So this you should have access to this code. I'm going to run make test now and see what the output is. It should be in the printed to template.s. So I'm going to run make test here. Okay, let's look at template.s. And we can see some label was in fact printed to the output. So we added support for compiling simple IR labels to assembly labels. So probably the simplest method in the whole assignment, but hopefully that helps you get started with completing it. Okay, any questions? All right, so good luck. Hope you all can do well on this. I'll see you all next Monday.